Okay, good evening class. Our discussion for tonight involves substitution, elimination, and redox reaction, which are three essential topics in Organic Chemistry 1. Here is the outline of discussion for today's discussion. First, we will discuss about the concept of the rate of reactions. Then we'll delve deeper into the substitution reaction in the context of alkyl halides, alcohols, and carboxylic acids. And under this topic, we have three subtopics, namely unimolecular nucleophilic substitution, or Sn1 reaction, for alcohols and alkyl halides. Next, we'll discuss about bimolecular nucleophilic substitution, or Sn2, same for alcohols and alkyl halides. And finally, we shall be discussing about nucleophilic acyl substitution, or SNAc, which is basically the main reaction of carboxylic acid and their derivatives. After the discussion of substitution reaction, we shall also discuss about elimination reaction, which also happens for alkyl halides and alcohols. Under elimination reaction, we have unimolecular elimination, or E1, bimolecular elimination, or E2, and finally we have unimolecular conjugate base elimination, or E1CB, which is under advanced organic chemistry and therefore not part of your lesson. And finally, the last essential topic that shall be discussed tonight is redox reactions. Basically, when we talk about redox reactions, we are referring to oxidation and reduction reactions of organic functional groups. Take note that the following aspects are not discussed in this video lecture as they are part of advanced organic chemistry lessons. Those aspects are, we have alkyl shifts in E1 and Sn1 reactions. We also have hydride shifts, and finally solvent and temperature effects for competing elimination and substitution reactions. First, we'll be discussing about the concept of the rate of reaction. For a hypothetical reaction, reactant A produces product B. The rate is expressed using this equation. We have rate is equal to K times the molar concentration of reactant A. This type of reaction is only dependent on the reactant, on one reactant. So therefore, we call this type of reaction a unimolecular reaction. In the second hypothetical chemical equation, A plus B will produce product C. The rate expression is given by rate is equal to K times molar concentration of reactant A times molar concentration of reactant B. Take note that the rate of the reaction is dependent on two variables or on two reactants. Therefore, we call this type of reaction bimolecular. So in the context of substitution and elimination reaction in today's video lecture, we shall be delving on the difference of unimolecular and bimolecular substitution and elimination. The common reactants that are involved in substitution and elimination reactions are basically we have reactants having tertiary carbon. This is a tertiary carbon because it's bonded to three alkyl groups. And then we have the secondary carbon bonded to two alkyl groups. And finally, we have the primary carbon bonded to one alkyl group. In the context of alkyl halides and alcohols, we have tertiary alcohol, secondary alcohol, and primary alcohol. Under substitution reaction, one of the reactions of alkyl halides and alcohols is the substitution reaction. First, the unimolecular substitution reaction is a reaction that occurs for bulky alkyl halides and alcohols. When we say bulky, we are referring to tertiary alcohols or alkyl halides. The term Sn1 refers to unimolecular nucleophilic substitution. So one is unimolecular. It means that the rate of the reaction is based only on one molecule or the formation of one molecule. Nucleophilic means that the reaction involves nucleophiles. And finally, we have substitution reaction in which one of the substituents is being replaced by another substituent, or is being replaced by the nucleophile. The general mechanism for this type of reaction is as follows. Suppose we have this organic compound with a good leaving group. When we say leaving group, these are atoms that form polarizable bonds with carbon. So therefore, because those bonds are polarizable, they could be easily broken. Okay, the first step for Sn1 reaction is that the leaving group leaves initially, which results in the formation of carbocation intermediate. Okay, so this is your carbocation intermediate, which is a stabilized carbocation for the reason that there are three alkyl groups that are bonded to it, and therefore they stabilize the carbocation through positive inductive effect. The last step of the Sn1 reaction is that the nucleophile will attach itself to the carbocation, which serves as the electrophile, and finally producing the final product, in which the nucleophile now substitutes the original position of the leaving group, of the good leaving group. Take note that the formed bond between the carbon and the nucleophile should be a non-polarizable bond. In the aspect of why this type of reaction is unimolecular, it's because the rate of reaction is represented as rate is equal to K, or the rate constant, times the concentration of the carbocation intermediate that is formed. This implies that the rate of the reaction is dependent on how much carbocation is formed, because the attack of the nucleophile to the electrophile is a very fast process, and therefore what holds bearing in this reaction is the first step, in which the leaving group leaves. Okay, so it's only dependent on one molecule, or the rate is dependent on the formation of one molecule. The second type of substitution reaction for alkyl halides and alcohols is what we call Sn2 reaction, or bimolecular nucleophilic substitution. Sn2 comes from the term bimolecular, meaning the rate is based on two molecules. Nucleophilic, which means that nucleophiles are involved in the reaction, and we have substitution in which the nucleophile will replace the good leaving group. Okay, the rate constant for this reaction, or the rate expression for this reaction, is expressed as such. So we have rate is equal to K, or the equilibrium constant, times the concentration of nucleophile added, times the concentration of the starting material bearing the leaving group, or bearing the good leaving group. The general mechanism, as you can see, since the reaction is dependent on two variables, or on two reactants, which are the nucleophile and the electrophilic species, then we call this type of reaction bimolecular. As for the general mechanism, we have a primary or secondary carbon bound to a good leaving group. Since this is a good leaving group, meaning the bond that it forms with carbon is a polarizable bond. So this reaction only proceeds in one step. So the nucleophile will attack from the back, thus pushing away the leaving group and then finally breaking off its bond to form the final product, in which the nucleophile now bonds itself to the carbon with a non-polarizable bond, or a stronger bond. In the context of alcohols and alkyl halides, Sn1 reaction could be interpreted as such. In the case of alkyl halides, the leaving group is the halogen. Okay, it's the leaving group, and therefore it has a polarizable bond with carbon. So the first step of the reaction, as discussed previously, is that the leaving group leaves initially, forming a carbocation intermediate. So the carbocation intermediate is a strong electrophile. Finally, the nucleophile will attach itself to the carbocation intermediate, forming the desired product. This is the desired product for this type of reaction. And take note that the bond that is formed by the nucleophile to your carbon is not a polarizable bond, or meaning the bond that is formed is a strong bond. The nucleophiles that could be used in this type of reaction are, we could have strong nucleophiles or weak nucleophiles. since we already have a strong electrophile, meaning even weak nucleophiles could react in this type of reaction. So for strong nucleophiles, we have fluoride, hydroxide, and alkoxide. So under alkoxide, we have methoxide, ethoxide, or propoxide. So whatever alkoxide base or alkoxide nucleophile they're in. As for the weak nucleophiles, we have water and we have alcohols. In the context of Sn1 reactions of alcohols, take note that Sn1 reactions only occur for tertiary or secondary alcohols. And one noticeable thing about alcohols is that the bond between carbon and oxygen is not polarizable. So how do we make the reaction happen? In order to make the reaction happen, we make the non-polarizable bond into a polarizable one by reacting with H plus or an acid. Okay, so after the reaction with an acid, what we form here is water. Okay, so this is water, which is a very, very good leaving group. Water will leave initially, forming a stable carbocation intermediate. So the carbocation now serves as our electrophile. And finally, the nucleophile could subsequently attack the electrophile in order to form the final product. Okay, so we could have strong nucleophile or weak nucleophile similar to the Sn1 reactions for alkyl halides. After the nucleophilic attack, we form the final product. This is our desired product. And take note that the bond between the carbon and the nucleophile is not a polarizable bond. Okay, the reagents that could be used in this type of reaction are we have hydrogen ion source and a nucleophile. Okay, this is the first type of reagent that we could use. A hydrogen ion source like sulfuric acid and a nucleophile in order to attack the carbocation intermediate, or we could have an acid with a nucleophilic conjugate base. Okay, so this is an acid with a nucleophilic conjugate base. An example of that is hydrofluoric acid. So the H there is the hydrogen ion source, and the F minus will serve as the nucleophile, which subsequently attacks the carbocation intermediate. Some exercises provided herein involves alkyl halides and alcohols. So in the first example, we have an alkyl halide reacted with water in the presence of heat. Okay, so if you see something like this, we are referring to heat. So heat is applied in this reaction. And the first step of this reaction is, if we examine the alkyl halide that we have, this alkyl halide has a tertiary carbon. Therefore, we could say that this type of reaction is an Sn1 reaction. Since this is an Sn1 reaction, a stable carbocation, tertiary carbocation is formed after the alkyl halide, after the bromine, which is a good leaving group, leaves the molecule. And then finally, the water molecule, which serves as the nucleophile, will attach itself to your carbocation intermediate and finally forming the final product. Okay, so this came from water, which served as the nucleophile for this reaction. In example number 2, we still have another Sn1 reaction for the reason that we have a tertiary carbon here, which means that a tertiary carbocation is formed after the bromine leaves. Okay, the bromine leaves, forming a tertiary carbocation, and then the nucleophile or the nucleophilic aspect of this molecule is this alkoxide reagent. Okay, this alkoxide reagent will attach itself to the carbocation and finally forming this ether product. The third example involves a tertiary alcohol. And in this example, we have a hydrogen ion source and a nucleophilic source, which is a fluoride anion coming from HF. So the hydrogen of HF attaches itself to the hydroxyl group of your alcohol, which forms water, and then the water will leave to form a carbocation intermediate, which subsequently causes the nucleophilic attack of the fluoride ion to your tertiary carbocation to produce the final product, which is an alkyl fluoride or an alkyl halide functional group. Okay, so our nucleophile here is this one. And the hydrogen will serve as the reagent that makes the carbon hydroxyl bond polarizable. So this bond is not polarizable, but because of hydrogen, this bond becomes polarizable. In example number 4, we have a separate hydrogen ion source and a separate nucleophilic source. In example number 3, the nucleophile and the hydrogen ion source is in one molecule. So this is our H plus source, and this is our nucleophile source, nucleophilic source. In example number 4, we have a separate hydrogen ion source and a separate nucleophilic molecule. So the hydrogen ion source will make the non-polarizable carbon hydroxyl group bond polarizable by creating water, and then the water will leave to form a carbocation intermediate, which in turn causes the subsequent nucleophilic attack of this molecule, of the methanol molecule. So this one will attack the carbocation and finally attaches itself to the carbocation to form the ether product provided herein. Alright, so this is the type of reaction that occurs for the Sn1 reaction of alkyl halides and alcohols. For the Sn2 reactions of alkyl halides and alcohols, take note that this reaction does not involve a carbocation intermediate. This reaction is a concerted reaction in which the nucleophile will attach itself to the electrophilic carbon and in a cascade manner push away the leaving group and attach itself to the electrophilic carbon, forming a stronger and non-polarizable bond. So in the case of Sn2 reactions are for primary and secondary alkyl halides and alcohols, and the reaction mechanism can be seen as such. So the nucleophile will attack from the back of the molecule. It's what we call backside attack. And as the nucleophile draws itself nearer to the electrophilic carbon, the polarizable bond between the carbon and the halogen will eventually break, and the non-polarizable bond between carbon and the nucleophile will be formed, forming the final product. The nucleophiles that we could use in this type of reaction are the following. So we have, for strong nucleophiles, we have hydroxide, alkoxide, and fluoride. For nucleophiles, for weak nucleophiles, we need heat, and we could use water, alcohol, ammonia, or amines. In the context of alcohols, still it happens for primary and secondary alcohols, but one noticeable thing about alcohols is that they have a non-polarizable bond between carbon and hydroxyl group. Okay, meaning this bond is, hydroxyl group is not a good leaving group compared to halides, halogens, and alkyl halides, and therefore reaction could not proceed easily unless we make the non-polarizable bond polarizable. So how do we make it polarizable? We use a reagent that makes the hydroxyl group polarizable. So let's, for the purpose of discussion, we call it LG reagent or leaving group reagent. And this reagent will attach itself to the hydroxyl group, forming this type of OLG group, which has a polarizable bond with carbon. So this bond is not polarizable. And since it is a polarizable bond, the nucleophile could now attack from the back and breaking off this polarizable bond between carbon and oxygen, finally producing the final product. The LG reagents for this Sn2 reactions for alcohols are the following. So we have SOCl2. SOCl2 is called thionyl chloride. We have phosphorus tribromide. And finally, we have TSCl or tosyl chloride. For SOCl2 and PB3, these reagents have built-in nucleophiles already. So for SOCl2, the built-in nucleophile is already chloride and ion. For PB3, the built-in nucleophile is bromide and ion. For tosyl chloride, it has no built-in nucleophile, so you could use any nucleophile subsequently. One aspect of Sn2 reactions, which is different to that of Sn1 reaction, is what we call Walden inversion or inversion of chirality. Take note that the nucleophile attacks from the back. Okay, the nucleophile attacks from the back of the molecule. So for example, in this hypothetical molecule in which there is a living group having this chirality, this is an example of an R enantiomer. Supposing that Lg is the first priority for CIP rules. So this is an R enantiomer. And take note that the nucleophile attacks from the back. So if for Sn2 reaction, the nucleophile attacks from the back, meaning it will attach itself from this position to push away this living group. Okay, so meaning it will attach itself here. Okay, so the nucleophile will attach here. This is what we call backside attack because it attacks from the backside position. So what happens when the nucleophile attacks from the backside position is that the resulting product will result to the nucleophile attaching itself to the backside position as well. So since the nucleophile attaches from the backside position, then this hydrogen atom will be pushed in the front and the nucleophile will form a bond in the back. So this is our nucleophile. This is the hydrogen that is pushed in the front. Therefore, achieving this or forming this type of conformation. And if we examine the chirality of this molecule, this now is an S enantiomer compared to its previous chirality, which is an R enantiomer. So this is what we call Walden inversion or inversion of chirality, which occurs for Sn2 reactions. Okay, so let's have some exercises for Sn2 reactions. So we have a secondary alcohol here reacted with thionyl chloride. Okay, this is our example number 1. A secondary alcohol reacted with thionyl chloride. The chirality for this molecule is we have 1, 2, and 3. So this is an R enantiomer. And take note that thionyl chloride is both an Lg reagent and a source of chloride nucleophile. Okay, so this is an Lg reagent which has a built-in chloride nucleophile. When we say Lg reagent, it makes the non-polarizable carbon-oxygen bond polarizable. And we have chloride which attacks from the back. So having this chirality afterwards. So if you examine this molecule, the chirality now is an S based on CIP sequence rules. So from R to S, this is what we call Walden inversion or inversion of chirality that occurs for Sn2 reactions. For the second example, once again, this is an R enantiomer. And PbR3 is once again an Lg reagent and a source of bromide nucleophile. Okay, so it's a nucleophile source for bromide. Okay, take note that because of inversion of chirality, bromide will attack from the back and therefore its bond is at the back. Okay, thus forming an S enantiomer afterwards. Okay, for example number 3, we have an alkyl halide. Okay, the bond between carbon and bromine here is already polarizable, so we don't need any Lg reagent. We can just use any nucleophile as is. So the nucleophile here is the hydroxide coming from sodium hydroxide. So it will attach itself from the back. It will attack from the back, forming a bond at the back of the molecule. So thus inverting the chirality from R to S. Finally, we have the last example is a secondary alcohol having an R chirality. But this time we have a separate Lg reagent, which is tosyl chloride, and a separate nucleophile source. So this is our Lg reagent, which makes the non-polarizable bond polarizable. So this is a non-polarizable bond, but after the reaction with tosyl chloride or the Lg reagent, what we form here is an OTS group, which is a very, very polarizable bond. So now the bond is now labeled as red, meaning this bond is a weak bond or a polarizable bond. And because of that, the fluoride could easily attach itself. The fluoride is a source of, the sodium fluoride is a source of fluoride nucleophile, causing the backside attack of fluoride to the molecule, thus forming these S enantiomer product. Finally, let's compare and contrast SN1 and SN2 reactions. SN1 reactions typically occur for tertiary and secondary alkyl halides and alcohols, whereas SN2 reactions occur in the context of primary and secondary alkyl halides and alcohols. Furthermore, SN1 reactions are stepwise, whereas SN2 reactions are concerted. And since SN1 is a stepwise reaction, it forms a carbocation intermediate, and since SN2 is concerted, meaning there are no intermediates involved. Another aspect of SN1 reaction is that during the formation of a carbocation intermediate, you will lose your chirality. Okay, so there's a loss of chirality. This is for advanced organic chemistry. And for SN2 reactions, as we have learned previously, there's an inversion of chirality called Walden inversion. For advanced organic chemistry, SN1 reactions also results in what we call hydride shift and alkyl shift, but we shall not be discussing these two concepts in Org-Chem 1. Okay, another type of reaction is what we call SNAc or nucleophilic acyl substitution. So from the term nucleophilic acyl substitution. Okay, so nucleophilic means a nucleophile is involved. Acyl means a carboxylic acid or derivative is involved. Okay, we have carboxylic acid or carboxylic acid derivative. Meaning, SNAc reaction is basically the substitution reactions of carboxylic acids and derivatives. So the general mechanism of this reaction is that we have a leaving group bonded to an acyl group. So this is what we call an acyl group. And an acyl group is being substituted by your nucleophile. So therefore, it's called nucleophilic acyl substitution. So the nucleophile will attach itself to the electrophilic carbon of the acyl group, thus pushing this bond upwards, and results in the formation of the tetrahedral intermediate. So take note, the leaving group has a polarizable bond. So as you can see, it is a red bond. And the arrow that I've written here is a blue arrow, meaning it will result in the formation of a stronger bond or non-polarizable bond. So in that formation of tetrahedral intermediate, this is the time wherein the molecule decides which group leaves and which group stays. So the one that leaves is basically the good leaving group because it has a polarizable bond, and the one that stays is the nucleophile because it has a non-polarizable bond. So the molecule will have this arrow pushing mechanism in order to break off the bond with the leaving group, with the good leaving group, and finally producing the substituted product. So the nucleophile will now substitute the acyl group, forming this type of product. Okay, the most common, this reaction is very much typical for carboxylic acids and derivatives. In the following slide, we have the different types of nucleophilic acyl substitution reaction. So let's start from the first nucleophilic acyl substitution reaction. Okay, so this is the formation of acid chloride functional group from carboxylic acid. So take note here that this bond is not polarizable, but since SOCl2 is an Lg reagent, or it makes the bond polarizable, and it has a built-in chloride nucleophile, so therefore the chloride will be able to attack this electrophilic carbon and form the final product, which is an acid chloride. So it will still follow the same mechanism provided herein to form the final product, which is an acid chloride. Okay. The second type of reaction, let's say reaction number 2, is the formation of acid anhydride from acid chloride. Okay, this is a functional group called acid anhydride. And in this reaction, we have reaction of this carboxylate nucleophile. Okay, this is our nucleophile, which is what we call a carboxylate nucleophile. Carboxylate nucleophile will attach itself here. Okay, so let's draw a blue bond in order to indicate that what we have here is what we have formed here is a stronger bond or a non-polarizable bond. So in this case, the carboxylate nucleophile will replace the chloride leaving group. So therefore, this is another type of nucleophilic acyl substitution reaction. Okay, the third reaction is the formation of esters. This is an ester. Esters from acid anhydride. So esters can be formed from acid anhydride through the reaction of what we call an alkoxide nucleophile. Okay, an alkoxide nucleophile. So examples of this, we have OCH3 minus, OCH2CH3, or an ethoxide nucleophile. Okay, so what we have here is that this nucleophile will attach itself here, and finally, the leaving group, the carboxylate leaving group will be replaced by your alkoxide nucleophile, and finally producing the ester functional group. The fourth type of reaction is the formation of amides, or the amide functional group. This is what they call an amide functional group. So in this type of reaction, what we have here is a nucleophile that is either an amine, or ammonia, or an amine. Okay, so these are your nucleophiles in this type of reaction. Or we could have an NH2 minus nucleophile. So we could have this strong nucleophile as well. So what happens here is that these nucleophiles will attach themselves here. And finally, the alkoxide leaving group from the ester will be replaced by the nucleophile forming the amide functional group. Okay, so of all these functional groups, the strongest bond is between carbon and nitrogen, followed by carbon and alkoxide, followed by carbon and carboxylate, and finally carbon and chloride is the weakest bond. So this is the strongest in terms of bond strength. This is the strongest. This is number 1. This is number 2, number 3, and the weakest. Okay, so therefore we could create nucleophilic acyl substitution reactions if we follow these steps, but never the other way around. So if we go upwards, say for example, we have amide to ester, and we use alkoxide nucleophile in order to replace the NH2 from the amide, then that will not happen. Or from ester to acid anhydride, we use the carboxylate nucleophile, it will not happen. Or from acid anhydride to acid chloride, we use the chloride nucleophile in order to form the acid chloride, that will also not happen. It's because the resulting product should have a stronger bond because molecules want to achieve stability. Alright, so these are the general mechanisms for SNAc reaction. Another special type of reaction which bypasses the formation of acid chloride is what we call the Fissure Esterification reaction. In Fissure Esterification, what we have here is a carboxylic acid. Okay, this is Fissure Esterification. Let's call this reaction number 5. Okay, we have a carboxylic acid reacted with alcohol in the presence of sulfuric acid. So what happens here is that sulfuric acid will activate this position so that the nucleophilic oxygen from the alcohol could attach itself to the carbon. Alright, so right now this is still a weak electrophile, but after activation, this carbon becomes a strong electrophile, and after becoming a strong electrophile, this weak nucleophile could attach itself here, and finally getting rid of this OH group after certain steps. So what we form here is an ester in the formation of in Fissure esterification. let's have some examples for SNAc reaction. Okay, so we have SOCl2. So we know that this is already for formation of acid chloride from carboxylic acid. Alright, so this is the reaction number 1 provided herein. Okay, so let's have acid chloride plus sodium methoxide. Okay, so this is formation of ester. Okay, this is formation of ester from acid chloride. Okay, take note that whichever combination, as long as whichever combination is possible, as long as it follows this uh, general scheme. So we have 1 to 2, or carboxylic acid to acid chloride, then downwards. So we have acid chloride to acid anhydride, acid chloride to ester, or acid chloride to amide. So we can have direct type reactions from these. So if you add NH3 to acid chloride, you will form an amide, or if you add alkoxide to acid chloride, you will form an ester. Alright, so let's have another type of reaction. Okay, so what we have here is the reaction of alcohol, this is ROH, and carboxylic acid. Okay, so in the presence of an acid catalyst like sulfuric acid. So as you can see, this is a reaction number 5, which is what we call Fissure Esterification. So the nucleophilic alcohol, this will serve as the nucleophile, will attach itself here after activation of this carbonyl position. So this carbonyl position is activated by your acid, and finally producing the final product. So this OH will be replaced by your alcohol. It will be replaced by this to form the final product. Okay, so this is the product formed by the Fissure esterification in this case. Alright, so these are some exercises on nucleophilic acyl substitution reactions. Okay, now let's go to hydrolysis reaction. Hydrolysis reaction is another variant of nucleophilic acyl substitution, but in this case, it's the other way around. So if nucleophilic acyl substitution is formation of carboxylic acid derivative from carboxylic acid, hydrolysis reaction is the opposite. So hydrolysis comes from the word hydro, meaning water, and lysis, meaning to cut. So we could say that it is cutting the bond with water. So which bond is being cut with water? The bond that is being cut with water is, alright, so the general mechanism is that we have water here because it's a hydrolysis reaction in the presence of acid or base and heat. Okay, so if you have water, acid, base, acid or base, then heat, and then you react the carboxylic acid derivative with these conditions, we will always form the original carboxylic acid functional group. Okay, so an example provided here is this one. We have ester functional groups here. Okay, these are the bonds of the esters. Okay, these are ester bonds. And if we hydrolyze this type of molecule, we have water, we have sulfuric acid, and we have heat. So what happens is that this bond is being cut and replaced by OH from water. Okay, this one will be replacing the bond, finally producing the desired product. Okay, so we finally producing the carboxylic acid molecule. Okay, so therefore these are the topics under substitution reaction in organic chemistry 1.